Aviad and there, and also text message from Nandini, and then I shared it with Camel. So I think we should focus on existing experiments to the extent which they answer these questions. And if there are open questions, then we should focus on the question of what new experiments would help settle the open questions. As you can see, as a theorist, I have put on the experiments, which actually is an important thing to do here in this talk. So I'll just go through the 4 questions then so that we know where roughly things are. One is whether there's a gap and pairing in the insulator, or could there be an electronic insulator of some kind, an electron glass? The other question is there an anomalous metal of some sort in these experiments, or some of them? Third question is, there are different ways to tune across the transition, and some of it is disordered, others, showed this morning, feel, and I think Claire and others had pressure. So, and the last question is about the nature of the transition itself, first order, continuous, universality, quantum fluctuations. So that's the, so let's start with the first one. As I say, there's experimental evidence for a gap and pairing on the insulating side of the SIT in many systems. But are there systems where this is not true and there is direct evidence for an insulator of electrons? For instance, in Matthew Fisher's phase diagram here, electron glass. Have anyone seen something like that? So what are the experiments that have seen that? And how do the materials which show electronic insulator differ from those that show a paired insulator? So I would urge all of you one by one to address these or related questions. I don't know who wants to go first. Majma, why don't you do that? Because you had the phase diagram of the electron glass, as well as you have evidence for paired insulators in some of your data, which you didn't show.
Okay. Also, what I would comment is that this field has been driven for decades with the aim to find some sort of universality in materials. And I think last decades shown that actually this is condensed matter physics, this is not AMO, and that details matters and materials matters, electron density matters, everything matters, and that there is a variety of scenarios. So there are materials where people have seen a gap in the insulator, and very important results. Aviad, for instance, of tunneling in indium oxide. I think you also mentioned gap measurements in iodine nitride. But you have also other families of disorderable superconductors that transit through a sort of metal, like molybdenum germanium. I'm not aware about the tunneling into the state terminating superconductivity. We may suspect a little. It's an apple. Yes, okay, good. At least superconductivity. We're already at 2.5 kilo and that.
It's just a matter. Is that actually well described by Finkelstein's theory?
The transition itself now.
Okay.
But for the approaching to the transition.
Yes.
And what are you saying with the systems that we don't see a gap in?
No, I'm aware about only about your measurements in indium oxide and this stuff, measurements in iodine nitride for the insulating part. It's delicate, it's not easy to make tunneling in insulator. You need to do it at the temperature to evacuate charge. But for other materials, I don't know.
So I have more of a question in this. Are there optics measurement of the gap in the insulating state? Insulating side.
Can you speak up a little bit?
In the insulating side. No, the other side, of course, there are plenty. That is why my question is, because tunneling suffers from some of the problems when you have an insulator. There is charging effects that come in, which and also if there are electrode effects that come in, because you no longer have a zero resistance electrode of a square length.
Depends on the barrier you use, yes.
But optics would not suffer from any of
So
these.
what are the, it
So
would
if you
be
want to do-
difficult to do an optics experiment.
The problem with STM is impossible because if you have charging, you would have crashing with the tip. So you have, if you want to do tunneling experiments, you really need to have the barrier of your sample much more resistive than the sample. Now you're trying to measure an insulator. You cannot go to too low temperature because it will kill you. You cannot go. You cannot go too deep in the insulator, even though it's dying now. So these are the kind of the limits that you have.
Yes.
In optics, you don't have these limits.
So optics, are there any limitations? Because you also do optics.
We only did it in the semiconductor.
I guess that's an area that one should look
That yet
at.
you're doing experiments on the tunneling into the insulating.
Yes, but
So I think that would
It's
be a
hard.
very important experiment. Those of you who have samples should contact the optics person to understand it.
Yeah, but it's complicated. It's dilution range, low frequency range, which is not obvious. So you shine a sample at dilution range temperature, which might be a sensitive guy. So what do you really measure? You know, it's like you measure a sensitive Josephson junction that you open to light. Might be difficult also.
And dilution would be difficult. Maybe a little higher temperatures would not be that difficult. But someone will have to try.
if your TC is 3 degrees, so if your superconducting is few degrees, you don't need to go to dilution. In indium oxide, in principle, I think might be 1.5, maybe.
I think the tunneling is already fantastic experiment.
Yes.
The gap was nearly the same as in the superconductor. I mean, we have checked that the tunneling resistance were bigger than the resistance of the sample, so it's a sanity check. And it's,
Is it possible to make these LC circuits?
Can you say it louder so
Is it possible to make these LC circuits that Benjamin was speaking about locally on a tip or something like that? Well, you know, people do squeedle things, right? That sounds simpler.
So I mean, I think Bina, is she here?
Yes.
Yes.
So I don't know if you were to measure a local superfluid density, what would be your resolution? Spatial resolution.
So the problem is that you always collect if they correlate. You can't limit the size of the probe is not what the limiting factor. It's the cloud. We did that with a very, very low superfluid in the Josephson junction arrays. And we see that the moment the superfluid is very weak, we actually sense a larger area than we think. So it actually goes larger in space than the weaker it is. And the clouds that we see extend to way bigger than the probe.
yeah. So one counterpart would be not local, but to make some sort of diamagnetism in the insulator. If you see a small diamagnetic response, which means you have local loops. We thought about that a long time ago to use piezo resonators in magnetic field to see perhaps.
Yes. Expect there is disorder in the system, so expect the superfluid to be strong here and weak there, and probably image that.
I would like for our studies, since we can use MD to grow central drifting fields. So actually, we studied one monolayer iron selenide like that grow on STO substrate. The TC could be onset TC larger than 40 Kelvin, times for high TC superconductor, and the thickness can be smaller than 1 nanometer. And that situation, indeed, we considered this important question. So we tried to do some in situ, in ultra high vacuum in situ disorder modulation on such ultra thin high TC superconductor, crystalline superconductor, and we actually deposited some cluster atom clusters, add atoms actually, artificially induced some disorders on film. Indeed, if we took the films out of ultra high vacuum system to do the transport measurements, we found with the increasing deposition, such clusters, and the film can be from a superconducting resistant state to insulating state, such as SIT can be observed. And simultaneously, we have low temperature STM. So we studied STM to see the local property of such a film. Of course, we avoided the clusters. We just put the tip on the clean surface, make sure the clusters are as far as possible. In that situation, we found for pure film or small disorder situation, we can see very good full gap, U-shaped gap for superconducting gap. And when we increasing the disorder, then such a U-shaped maybe becomes like a V-shaped or like that. And
on the insulating side?
Not yet, but if we pushed it to insulating side by our transport, demonstrated by our transport measurement, then we found a very large, not very large, but larger superconducting full gap, larger than superconducting state situation. So, and sometimes it's not symmetric or like that. So we discussed with Natalie from Ohio State University. She suggested it's a kind of a Cooper pair gap, and but you have to consider some electron local correlation or like that. So that's our recent work. We tried to answer this question from our sample system. In our system, it looks like it's a Cooper pair insulator, but it might not be very universal for all kinds of 2D superconductors.
So I guess one question for the experiment is, what is different about molygermanium compared to, say, niobium nitride or indium? I mean, I know you can say the chemical formula is different, but I want to understand in terms of physics, what is different?
Molygermanium is an amorphous superconductor.
Okay.
As opposed to niobium nitride or titanium nitride, which are actually crystalline or polycrystalline. That's definitely one difference. Indium oxide, I don't know. It's a complicated object. Is it always amorphous? Because it also has crystalline phases.
Well, it's V over here.
Exactly.
No, but
It's V over here who has a paper
Where you see
these
it
40
becoming
phases of.
even more amorphous than the amorphous one.
Yeah. That is why
you can go maybe phases. You are made up above 60 degrees Celsius and it crystallizes. And you have clusters of indium. People who investigated indium oxide with indium crystallite inclusion. It may work on this, but it's a very different.
No, but I think the one you're using and the one Aviad is using is amorphous, and you do X-ray diffraction.
Crystalline phase of indium oxide is not superconductor.
Yeah.
It's not
It's a very dense germanium.
Large electron density.
Yes.
So you have parameters that change from the metallic point of view. Okay, normal state point of view, that matters.
Okay.
How high?
When you say amorphous, you mean the morphology is amorphic. That's not.
No, it is.
It's not the structure, right? Even if it's the
Not the structure for molybdenum germanium.
it is the morphology.
It is a structure which is completely amorphous.
Right.
If you take extra diffraction, you will not see a peak.
And indium oxide.
Same.
Also,
I don't know.
The same. But
No,
you
but-
measure locally, you will
No,
see.
gallium nitride and titanium nitride are polycrystalline.
These are polycrystalline.
So that's I think that's what you were
I
saying.
just want to warn that even if the morphology is, smooth, you may see different electronic probability.
yeah, sure.
No, but he was
You
asking.
may have
he was
grains
asking
of
for
superconductors inside the
Electronic.
not.
Yes, of course. That's the.
That
That is
important to say that.
Indium oxide, niobium nitride, which is crystalline with still lots of disorder and scattering. the graphs on the slide, you cannot distinguish amorphous from crystalline.
I see. And they are very different from the molybdenum germanium.
And molybdenum germanium, I think the big distinction is the convexity, which is larger.
So maybe this talk would like to say something.
Yeah, I just wanted to ask about that. How high can you get the sheet resistance in the 1 inch?
Sheet resistance 2 kilo, 10 kilo ohms. That's good.
And then it is still superconducting, I assume, is it?
Yeah. Right.
Yeah.
2 kilo.
It's the period 2.5 kilo.
And this seems not to be a universal result.
That's not.
There is no, you do not.
No, it's not universal, but this is the value for molybdenum.
There was a war. There was a war where Henri Roquette studied molybdenum germanium. He changed the substrate. He put a germanium buffer. He did not put a germanium buffer. He put luminosity. And you change the substrate, you change the critical resistance.
Also, so the normal state is still modified.
How do you compare? For same thickness, yes, maybe yes.
You have different phonons. Well, it's fine. You have now. Wow.
So can go to high level.
It should be maybe Pratap last word, then we go on to the
So
next.
one of the things that we had observed both for niobium nitride and molybdenum germanium is that when you start putting in disorder, the initial suppression of TC decreases, but the initial suppression of TC appears to be fermionic in the sense TC scales with delta. It is, but in both cases, when you go to strong disorder, at some point TC keeps decreasing, but delta roughly remains constant.
But then if it goes to a metal, delta must collapse discontinuously.
Yeah, so it does not. It is a bosonic.
But then that can't be the description of molybdenum, unless you say that
Molygermanium originally, so our reason for studying molygermanium was precisely this. Molygermanium was considered to be one of the classic system where Finkelstein's theory is valid. We realize that that's only valid within a range. At very strong disorder, it is
Now to have grains. So Finkel theory is for both. No grain, no.
No. Molybdenum germanium is completely amorphous.
I think that's the point.
I want to make a different remark and a suggestion. Namely, so we have discussed some of the materials, but Claire's system is one of those that shows these failed metals, failed insulator behavior. And maybe I have transitioned.
that's the next question.
I think what would be interesting is if you would perforate these films and see whether you see little Parkes-like oscillations on both sides. This is one of the classics which has not been done on many systems yet.
Is niobium silicon.
Yes.
So, okay, I think it's a very good segue into this question of the anomalous metal. Thank you, Gustav. Is this just an artifact of the filtering in the transport measurement? If not, what is the difference between materials that do and do not show anomalous metals? Are there measurements other than DC resistivity characterizing the anomalous metal? And even if this is a filtering artifact in at least some materials, does the existence of this, showing that the system is extremely fragile near the SIT, give us some new insights into those systems? And is the anomalous metal related to the state seen in the Kravchenko experiments? So those are the set of questions. Maybe Claire, you should lead on this.
Okay, so actually, a bit of context. I think initially when with Avian we wanted to put up this conference, it was also a way to combine the community from the 2D systems, where this kind of question seems to be, yes, of course, a 2D metal exists, and the disordered community, when it has been really debated. So 10 years ago, when we 10, 15 years ago, a long time ago, when we showed that we were measuring metals in 2D, this was discarded as artifact or artifact. And since then, I think there have been many evidence in different systems, in amorphous systems, in crystallized systems, that they all show the same kind of behavior. So I definitely don't think it's a filtering issue. I think people by now know how to filter the crustat. Some samples have been measured in several groups. I've sent samples to Christophe. I've sent samples to Danny Shahar when he was still in the field, and all measured the same thing. It was induced by thickness. It was measured in our case in Navium Sulcate by on a single sample by annealing the same sample. Recently, we did some pressure experiments with Avia showing that in indium oxide we have such kind of anomalous metals. So yeah, I think we should understand what's. I agree with the questions. I'm not sure I have a clear answer to those, but yes.
So when you say anomalous metal, what? No. Phenomenologically, what is the description?
So R goes to finite value in the limit T goes to 0.
But before that, it has a drop. Is that drop essential or not?
So either it has a drop in the resistance, or it saturates. It's sort of weakly localized and then saturates, and it goes continuously from one behavior to the other. So you have superconducting, then you have a sort of superconducting thing that saturates at finite value, and then progressively it increases. You have weak localization and then saturation, and then you have an insulating regime that is first completely activated and then fermionic. So that's what I call metallic. Whether the dropping one and the weakly localized one are the same phase or not, whether it's still really a phase, I don't know. So this is.
So how many materials is this scene? The one you did originally was
Navium silicon, but that was
Now
not the
with
same.
Navia-
This was the only one. I mean, Rhodium germanium, and then Kapitunik showed some.
I thought the filtering issue, but maybe I'm wrong.
No, just a comment, because it looks like again the universal behavior. But there have been different regime of anomalous metal. Yes. What you are talking is zero field.
Zero field. So most of the experiments have been done under
original
field.
story came with the mixed phase.
Yes.
Yeah. So I'm.
This we should perhaps
Okay,
forget
we have
physics.
a discussion of that. Absolutely.
So this one is B equals 0.
I should have said that more clearly. Thank you.
So I don't have anything to say about P equals 0.
Okay.
So,
No, but I'm not the only.
Christophe, would you like to add something to this question?
I think they're not really. I mean, there are many observations were in finite field, and if you look how many were in zero field, it's maybe a handful, maybe not even a handful. Right? It is yours. It is the tantalum nitride, I think, at some point, and then it already stops in my.
There's quite a few.
No, there's Nadia Mason also. No,
Well, that was a Josephson junction array on a copper plane.
No, there were nano-perforated. No, it was Naive Islands on the graphene thing.
No, this was in it was on a normal model. So they say these proximity type systems, there it is quite regularly observed that you get these circulations. But it's evidently a very different system. In particular, the parent system starts as a metal, which is very difficult to convert into a insulator.
We've heard here, and we'll hear again about if the 2D monolayer crystalline centers.
Yeah. But this is in magnetic field, isn't it?
I don't think so.
At least in the first.
It's only in magnetic field.
I know the Dasanina is with video.
So
yeah, but I know like Jianwang, he mentioned like now I was saying like can show this at zero field.
monolayer.
So we studied all kinds of single crystal to be superconductors, and as Dean mentioned, ion selenide film, monolayer film, we also see very high, so very strong evidence for such as resonance saturation. Actually, the saturation temperature can be as high as 20 Kelvin. So that's you don't need to worry about noise from outside environments or like that. So for the YB cell system, actually we fabricated nano patterns, yeah, and also we use high quality filters, and we didn't see any different. It's not from a magnetic field induced. It's just a nano pattern. Like last speaker mentioned, the nanopore modulation, and with the etching time, increasing etching time, that means more disorder. Then you can see such a quantum phase transition, and still can see quantum so-called unknown metal state at ultra low temperature, 50 millikelvin. So it's a good way. High TC can show very high TC. And then you use a dilution temperature, you use high quality filters, maybe can give a more strong evidence for such a state. Yeah, that's our opinion.
But my impression is what is important is the value of the sheet resistance. If you have a metal film of 50 kilo ohm per square, it will all say of 50 ohm per square, then it will always be anomalous. You cannot convert this at moment accessible temperatures into an insulator. So you really need something that has this several kilo ohms of sheet resistance, and so that this physics can become active, right? That the localization with help of interaction and so really takes place at some point.
So critical reasons for the ideal situation, of course, people always say 6.45 kilo ohms, but it's for very ideal situation. It's like work as in real situation. Actually, whatever is lower than this value is very small value or much larger than this value, we can still see in some kind of disorders, we can still see such a resistant saturation at a very small value, at approaching zero temperature. Yeah.
Yes, but what I wanted to say is for most of the 2D crystals, which are not from the originally disordered community, for those crystals the sheet resistance is below 100 ohms. And then you should not be surprised that this is not localized.
But still, so then we have to explain how it can exist.
So the explanation of anomalous metal that kind of floating around. Imagine that part of the sample become metallic, and then you just measure. Some parts are superconducting, so the conductance is better. Some parts are metallic. There is no path that shunt the sun to the
You said exactly what I wanted to say.
Okay, so I want to hear what is your opinion about that.
Suppose you have, so I have always thought about first a very simple model to try to understand. If I have, let's say, superconducting grains which are coated with normal metal, I will always see an anomalous metal, because at some point my superconductor will become zero resistant. All that will remain is the normal metal part. Infinite resistance as you go to low temperature. So I wonder whether this huge confusion of anomalous metal, which is mostly on disordered systems, where such composite scenario can exist, is driven by that.
When for that, you should have a proximity effect, so the resistance should decrease on temperature.
Those are matters of detail. Proximity effect has some length scale, depends on disorder, what is the normal metal coherence length, and so on. So it may or may not work to give you a zero resistance. Depends on how thick that is.
It may happen this proximity may happen at very low temperature.
The range
is not accessible.
If you are just a little disorder, very tiny change of local disorder will turn your stuff into a metal side. So you can have inhomogeneity with a very small variation of properties of your field.
Exactly. That's the.
And then you have resistance in series. Things on that.
So usually, as Claire says, in many of these systems, it's not only the failed semiconductor, it's also a failed insulator at some point. I don't think you can explain, but it looks like an insulator, and then it kind of
That was my question as well.
Because insulator, I don't know. I'll have to think a little harder with a parallel resistor network model. If you have metals and insulators in a particular configuration, yes, I think maybe the first way to approach it, the first cut, would be to try to make parallel resistor models where one can see whether it is clear.
Right, so somehow it would have to be self-consistent. I think you said you made this this estimation.
Yes, this is one thing proximity effect already was mentioned. Also, I've seen the Hall effect. Like if you have like a metal with superconductor doesn't produce, but the metal should show some Hall effect. But people don't see this Hall effect in the almost metal phase.
Are there a lot of Hall effect data? I know there is one by Capitul, but
yeah,
are there other Hall effect data which have looked at it?
There are more and more.
All kinds of to decrease in superconductors, we can see
slow density for films.
at such normal, at such an enormous metal state. Yeah, we can see core starts to become zero, yeah, like that, and still you can see longitudinal residual resistance.
That will possibly not.
And this is a low field, very low field Hall.
Yeah, sure.
So your model is like having a superconductor and that having in series a metal, right?
Yeah.
Take superconducting balls, put
Yeah.
it
Okay. So, but in the end, it always amounts to what is this surrounding in metal?
Exactly. Good metal.
Is that obvious? Sure.
that is, I don't know whether that is the origin of any of this.
You know, in disordered. So the standard, as we all know, standard theory is that there shouldn't be any metal.
Thermodynamic.
Yeah, so that's with interaction. So then do we?
All systems have interactions,
Okay.
whether
So whether
You know, here TC goes to zero and metal and just.
Within a random resistor network, you can have this.
Sorry, please.
Sorry,
Go ahead.
within this random resistor network model, you can actually have this drop. It's just the fading of the superconducting transition is just given by the fact that you don't have a percolating path throughout the sample. So that's from coordination.
If we do that at very low temperature, we expect everything to be coherent. And also metal, the proximity effect between the grain and so on.
Question is, this is the way we explain the insulators. What's the difference between this metal and the insulator? Why do some systems show this metallic behavior and others goes directly to
in between can have.
Yeah, some
Finite resistance or very large resistance.
If you have an insulator with superconducting percolation, you have no coupling between the islands. At one point, you're limited by the psi of your islands, which is not the case if you have a metal. If you have a metal, you're limited by the covalent strength in the metal, which is really different picture.
So one comment added is we actually studied the zero Hall resistance, and simultaneously we can see is a H over 2E quantum oscillations for such an anomalous metal state. Then it looks like the Cooper pair dominates this state.
In which material?
YBCO and the iron-based superconductor and the nickel superconductor and others. I don't know. Maybe I don't know if Ding has done something in other systems. But in our systems, there's three kinds of high TC crystal thin fields.
So by the way, in your system, when we see in the insulator the quantum oscillation, does it also saturate at a finite temperature? Oh no, it goes into but that also saturates at a finite temperature.
It also shows on this.
I think that observation is something that is, to me, I don't yet understand it. Jim Wallace first saw it, the quantum oscillation in the insulator. And then other people are also seeing it. I think that
you don't mean quantum oscillations in the way mental physicists use
well,
it.
quantum oscillation means little
Not the
parts.
Gaussian
Little parts.
Little parts. Thank you. Yeah, we shouldn't call it quantum oscillations, brother.
No, okay.
Yeah, okay, no,
that is the one.
yeah, yeah.
The little part is exactly matching with one influx quantum.
That only means you have a scale at which you have a superconductor.
Yeah, so that part
Globally
is, of
or
course,
locally.
At least for high TC superconductors, the cross length of a Cooper pair is small. So in our initial consideration, we can consider it's a particle with nanometer diameter or like that. Then we can study from an AD effect or like that. By doing similar theoretical analysis, we can estimate the phase coherence length of such a nano-patterned 2D superconductor. Then we found for, of course, for superconducting state, it's infinite. And for insulator state, it's almost zero, because it's very localized Cooper pairs. But for so-called anomalous metal state, actually the coherence length is a short range. It's not localized, but it's not a long range. It's several hundred nanometers, like that. Then the cell power can show.
so how do you calculate that? How do you calculate the coherence?
Oh, like analyze the amplitude of the H
so
over
you
2
derive it
calculations.
from that.
Yeah.
But is there any cross-check of, is there any theory to cross-check this?
So our theoretical collaborator just like copy or from the AD effect, use the theory, AD effect theory to do such a calculation. But to consider high TC superconductor Cooper pair is small, so we can approximately use that model to do such calculation.
It's AB.
I don't know.
I don't know.
Okay.
Yeah.
The little parts.
A little less, yeah, little less.
Okay, do we need to add anything? Would anyone like to add anything?
So I'd like to ask if anybody has any idea why some, let's say it's a real effect, why some materials show it, and other materials will have a direct transition from a superconductor.
Condense matter. Every materials is different.
Okay.
You pick a material iron,
So give us
iron, strontium titanate, for instance, you have a huge
You can't give
dielectric
us
constant.
You can't
The
give us,
substrate, wait, you have a huge dielectric constant. The substrate has thin Coulomb interaction. So you cannot compare this material with another one because you have a different Coulomb interaction. It's fairly liquid. It's, you change completely the environment, everything. So you cannot compare apples and banana, I'm afraid. So everything is.
when we try to think about some conditions that would actually.
That's the
Okay.
Can
do
we break it up into some subsets?
There is also something else, is that when you make these nanopores arrays on alumina membranes, for instance, and things like that, you can see on the picture that we have seen, you completely change the topography and the structure of the film. So even that, I'm not sure you can compare, for instance, the French bismuth Jim Wallace on nanopores membrane to the French bismuth ultra thin, ultra flat. So each time it's.
Can we together as a community try to think of conditions that would lead you to a metal? Then we can check.
So I think it was applied in the previous discussion in economics. And like spectroscopy, if you see something in the spectroscopy in your metal, it's not metallic.
Local measurements will help to understand what is happening, and if we accept this picture that there is some metallic material that percolate, also within that we have insulating places that later on.
I'm asking you as a theorist, when will I get to this direct transition from the superconductor to insulator, and when will I get?
So imagine that you have this metallic environment that in holes of which are superconductor. And within this metal, you have regions which are insulated. So you can imagine a transition between the insulator just imagine that you have smooth potential, and DC in this region is bigger or smaller. So then when you lower the temperature, some parts become superconductor, some no.
And in the not parts, is that an insulator that is locally localized?
He's making a theory where it's a metal. He's just positing it. See, theorists can always come up with an explanation, but
Yeah, that's my point.
and I can say that. But I also want to say that I don't think we should view condensed matter physics as stamp collect. This material does this and that material does that, because the power is that if you look at the history of success in condensed matter physics, we have been able to say that this subset of systems does this and that subset does that.
We make categories.
Yeah. So that I think is what we should aim for.
My question was perfectly answered. Especially you asked if justice, I would have.
Okay, so should we move on? So the next thing was about different ways of tuning the transition, but since especially we are discussing the anomalous metal, I think we should first turn to why are anomalous metals, or why have anomalous metals been found more in field tuned transitions than in other things? If that's what I seem to understand from, did I understand that correctly? And if so, why?
It's a question of the magnetic field, what magnetic field does.
So, I can report facts.
Yes, please.
Not slogans. We measured pages where we used to characterize sensitive mesoscopic devices like junctions with critical current on the nanoamp range. For those who have measured that, knows that it's very difficult. Just a reminder, if you want to measure the Ange-Bauer formula for the junction, SIS junction of a transmon, which is about 20 nanoamps, it's very difficult. You can find a paper of Michel Devoret and perhaps one or two, but it's super difficult to get the right critical. So it is delicate. We are not at the level of Michel, but we do what we can. In the whole story, there have been claims of saturation that I showed molybdenum germanium and indium oxide. Indium oxide saturation at 1 Kelvin, which is for us nonsense because we have never seen that. We do not see any saturation in molybdenum germanium and indium oxide. So I can show my filtering scheme. What is a high quality filters? This is not a scientific argument to say I have a high quality filters. You need to quantify and show me a device that you can say, well, look, I'm measuring IC of 2 nanoamps critical current. And yeah, but this is the point. This is we have to be quantitative. And the point is that in this disordered indium oxide and molybdenum germanium that I measure, we could trace no saturation of the resistance. Also, you have to take some precaution. You have to put a thermometer on your sample holder because you have plenty of radiants that are usually don't take care of this legal issue. Then I don't see saturation. I stop here for the materials. For the other materials, I let you guys tell what you are. So crystalline superconductors was treated by Corridin and Danchar in Columbia University. They showed that if you put filters, this metallic state drops. Then it drops not fully thermally assisted flux flow. So you can wonder, so then here I have my anomalous metal, but then it's nonsense. Where do you see the, how do you qualify your filtering, your sensitivity? So it's about vortices, so pinning may matter. So can you compare disordered systems and crystalline? I'm not sure either. So this is where, again, we have to be careful with each system. For what concerns disordered thin films,
yeah, it's true. Yeah, it's true. So because the filters can be better and better, or like that. And so one way is just to use better and better filters at ultra low temperatures. The other way is just study the sample with the high temperature anomalous metal state. For example, 10 Kelvin, 20 Kelvin, you just use normal filters, it's okay. You don't need to worry about noise from outside. But if you study a TC around 1 Kelvin, then you study anomalous metal state at 0.1 Kelvin, then you should consider much for how to try your best to exclude the noise affection like that.
So it's not we're back to the discussion for those who were there. We had about 10 years ago in the Villard de Lans conference, where everyone was arguing it's filtering, not filtering. So I have the same basic answer. So everyone who wants to measure our sample is very welcome to provide them with some. I've already sent some samples, and let's compare. Let's solve this bloody issue of filtering. I mean, this is impossible to have the same debate 10 years after the fact.
You see, we have new data. For instance, the superfluid density I showed, it drops till HC2. So you did not pay attention. I did not insist on that. But the very last point gives superfluid stiffness, which is belong to the Josephson energy, of about 15 millikelvin. So 15 millikelvin in terms of current is 1 nanoamp. Do you think it's easy to measure a superconductor with a current of 1 nanoamp? In transport, I think it's nearly impossible. You plug something, you are.
Our experience more than 4 Kelvin or like that. It's if you add filters or not any filters, the results are almost the same. But of course,
then you don't have a sensitive material.
But if your anomalous metal state temperature is much higher than 4 Kelvin, for example, 90 Kelvin, so you don't even worry about it. And also, we discussed with Shaha. Shaha is the first person to do such an experiment. Actually, I invited him to visit our lab to discuss his experiments and our experiments. Yeah. Then he actually is open mind. Yeah, he can accept other cheating or like that.
There is a very good also example that we all know. Again, I come back to Onge-Bauer formula for a SAS junction. Measure the junction of a transmon. You will never get the Onge-Bauer formula by far. You get half for very small critical current. Okay, you put the electrons, you put the world, the environment to your junction, you will never measure IC. Make spectroscopy of your isolated transmon, you get the right Josephson energy. So transport for very delicate and fragile superconductors like mixed phase at low temperature, you got for HC2.
No, because you're thinking of a field.
We are in the field. I'm not discussing the other one. The other one, I don't think there is artifact in the same way.
Measure them together.
I don't think there is artifact for the zero field one.
Yes, so the question is still there. So what's
I'm talking about applications that show for the same material that I've studied since 20 years, saturation at 1 Kelvin. I have never seen this finished, so at some point it makes confusion, unfortunately. It creates confusion. There might be good physics, but it creates confusion.
For me, starting the moment you can have vortex tunneling, even with really good filtering and complex motion, even with filtering, means that you have dissipation link paths. So in principle, you should be able to see a metal if you have dissipation.
I agree.
I don't understand your point. I don't understand your thermally.
But dissipation can be from both outside and inside, intrinsic and entrance. Yeah. So we should be careful, but we shouldn't simply exclude the possibility of intrinsic dissipation.
But vortex would.
10 years back, the meeting that you mentioned, I was there.
Where was this?
And at that time, we had communicated a paper with anomalous metal. We withdrew the paper and repeated the measurement with filter. It disappeared.
Yeah.
After that, over the last 10 years, I have been trying to look for anomalous metal on every sample that we synthesize. I've never seen it. That's my experience.
The field one, the field induced one, or the zero field one? Important.
Neither. Neither. I have not been able to see. Whenever we have seen, in fact, Shulagna, I think, saw something at some point, then we put filters, it goes away. So we have to keep on tightening our filters. 40 kilohertz does not work, we go to 100 kilohertz, we go to 100 hertz. At some point it disappears. But another thing that I want to mention is about the suggestion of measuring samples with higher DC. I think that's a good thing to do if you are looking at zero field anomalous metal. Field-induced anomalous metal will not care because we will be exciting the vortex system and you can excite them even at hand.
Our result for most results of that is
Zero field, yeah. Okay. That is.
So another question is that if you tune across the transition in different ways, with disorder and with field, are you ending up in very different insulators? Or are those insulators somehow adiabatically connected? I know that's a very theory way of raising the question. You can interpret it suitably and in an experimental way.
The first, for me, tuning the disorder is a very vague word.
Okay, so how about sheet resistance?
Sheet resistance can be tuned in through thickness.
Yes.
Or through changing the material.
No, let's stay the same material change.
No.
Changes.
Yes. Okay. So and then so what we showed is that tuning. So our favorite system is Navier solver. So we can tune it either by thickness, heat treatment, or composition. Let's say simple.
Okay.
We tune either through heat treatment or thickness, and it shows a very different approach because thickness is different. Changing the thickness does something to your field.
So it doesn't just depend on the normal state sheet resistance.
Yes. And
okay.
Maybe I have a question. I actually seen a lot that in the whole disordered superconductor literature, thickness is always treated on the same footing as disorder, and it's always substituted one for another. But I've never understood exactly why is that as a theoretician. It doesn't make any practical sense to me. If there's anybody who can explain me.
Yeah, me too.
So
If you're really in the 2D limit, we can argue what the 2D limit is for, depends on the question in mind. If you have some kind of scale, but once you're below it, the only thing that, so changing the thickness in that case means changing the disorder. The same thing, because, the dependence on thickness only matters if you're 3D. But
you are always quasi 2D, right? You never.
If you're quasi 2D, so changing the thickness is like changing the disorder.
Right, depends what it's called.
You just reformulated my statement.
I think that one of the reasons, this may not be exact, but one of the reasons is that when you are at that kind of thickness, the surface defects start playing a more stronger role.
yeah, it should be.
That is the primary reason.
So essentially you're saying that, first of all, apparently for your explanation to work, I need the thickness to be smaller than the coherence length, or at least comparable.
Yes, of
Firstly,
course.
and primarily. And secondly, in this case, what you are saying is that then surface treatment starts to play a role, and as I decrease thickness, it will have more pronounced effect on the environment. But on the other hand, then it seems like a natural step just to, let's say, unpack your favorite Usadel equation and just show it by computing. And if it feels like it's not exactly that anybody has done this. And maybe I'm too young to know that.
No, but the thing is, I think this physics is beyond Usadel equations. But let's not discuss theory. Let's discuss the experiment.
Yeah, but I mean,
I'm discuss with you later why all of this physics is completely beyond Usadel equations. But let's not discuss that right now.
Yeah, actually surface and the interface of scatter is stronger and stronger in thin fields. So this water.
Yeah, I think that's the reason.
But then it is a different kind of disorder than the one that usually strongly disordered community is talking about, because it is the latter is about either impurities or amorphous structure. So it's intrinsically a Bach property.
And it is now clear that you cannot substitute one for another. It's just two different knobs, two different effects that you can, well, to some extent unite in certain physical situations, but not at all of them.
I think I understand your reasoning, but say in our experiments and also when comparing to perturbs, if we put the sheet resistance as the independent variable, we always get smooth curves.
No, what we have compared is in our experiments, we have compared the KFL values that we derived from 3D expression.
Already
So
seems
now
questionable.
KFL is an effective thing. I don't know where the disorder comes from. It's some average one. And we have seen that for KFL, we get a more or less universal, whether we are actually in IBM nitride putting in IBM vacancies or we are reducing the thickness. Beyond that, I don't know whether they are identical.
And this is for films that are thin compared to 3D coherent length.
Yes, so let's say we compare 3 nanometer films, which is much lower, with half the coherence length, and I compare similar KFL films with 200 nanometer. We see that the TC, for example, are similar, very close. So this, in some way, the disorder, though they may be different in origin, for example, 200 nanometer disorder would be very different from what I have the origin of disorder in 3 nanometer. Their effect on the TC is roughly the same. This is what I observe.
I want to say, let me make an experimental point. These transitions are happening when KFL is of order 1. Therefore, Usadel and
yeah, sure.
Azins
I'm not mentioning Usadel.
Yeah.
I'm just saying that this is a very it's at least the simplest first step to make, to examine at least in this large case.
Those equations assume KFL much greater than 1. So please
know that.
We have to remind ourselves that the sheet resistance is not only disorder, it's also electron density, and you can tune the SIT by electron density like we did in gating with Wilhelm Goldman. So the sheet resistance is not a good parameter to discard.
But KFL includes electron density also.
KFL is not the alpha square. Alpha square is kind of, it entangles both.
Yeah, okay, there's a bike, it's 3.
That's KFL essentially.
KFL is the disorder.
Yeah, KFL not disorder. Okay, like
No, the 2D limit CFL and our sheet resistance. So what I'm saying is that in our system, sheet resistance, you can have different sheet resistance, same TC.
Because you're
Because I'm
changing
tuning
the
different stuff.
Yes.
About weight. So you have a metallic plate above, that can also change the problem. Any experiments in this direction? Yes, the superconducting. Know that screening gate. Or, actually, it will influence
Screening lengths.
not only thinning, but it will also affect the housing of vortices.
Yes.
So no, because it's different when to tune post the transition. So I'm proposing.
That is something we could try. We have seen, for example, that not as a controlled experiment, but we can do that. We put sometimes capping layers, and capping layers actually change the level of pinning, vortex pinning.
Yes.
Now, how much it affects the electronic disorder in terms of scattering, that we have not checked.
Affect the transition, because we discuss proliferation of vortices. But now when they hop, they change the properties of the metallic state above them. So it will be more difficult to count.
Probably it will. I think a controlled experiment in this direction would be interesting in many systems, in various systems, to try to put in these ultra thin films, to put capping layers and see, for example, if it even affects the SIT or SMP, all these quantum phase transition that
it should.
So, Tristan, would you like to add something to this discussion?
Oh no, I think I can say something.
So, question is a clear question, I think.
Okay.
This one that I think you may agree that they are supposedly different positions.
Could well be. But I just asking what is known experimentally because people study different parameters. So
I would just say that if you compare what happens in magnetic field, you put magnetic field and you destroy the superfield stiffness very rapidly and very strongly, and then you have a transition to something we don't know, we don't understand. That seems for me not obvious, but it's also for me different from the zero field case where, okay, we have proliferation, we have this vortex anti-vortex pairs that are bind, and we increase this order, you may have more and more because superfield density is dropping. Then suddenly we lose superconductivity, but the vortex class is certainly a different animal to take into account. Another energy scale may happen.
thank you.
Let me add that the pressure, you want to, yeah, go ahead. Yeah, you tell us.
I'll just say that since you mentioned pressure here, these are new experiments that we're doing, and there's going to be a talk on Friday. Pressure is different because pressure can do two different things. If you talk about a granular system or an electronic granular system, pressure can on one side decrease the amplitude of superconductivity in each one of the grains, but it can couple between the grains. So it kind of acts in two different directions. So it's a new kind of cool tuning parameter which does different things.
And in indium oxide, so so this metal state, whatever you want to call it, has not been observed. I don't think either in thickness or in the field or ever, and under pressure we see it.
So what is pressure you see it? How much pressure do you apply?
Gigapascal.
So
10 gigas.
Well,
that way.
So this is hydrostatic pressure on a thin film. Is that what you're doing?
It's a thin film, so define hydrostatic pressure. Can you
Okay,
apply hydrostatic?
That was, I guess, my question.
That's a philosophical question. Yes, we put it in a hydrostatic kind of environment, but it's a 2D film. So tell me what it is.
Okay. No, I have no idea. Okay, now should we do the last question or should we break, Aviyad? What is our plan? You guys should take that ball.
Since we're on the last question, that's just
okay. Okay.
So
the last question is about the nature of the SIT. Christoph raised the question of what is the nature of quantum fluctuations. Then there's the question of is it really a continuous state transition or could there be a first order transition? And if it's a continuous transition, does one observe universal critical exponents? I think there's one sort of general problem which seems to permeate that. Matthew Fisher suggested that there might be some self-duality and therefore the critical disorder would be universal, but he would be the first to admit that there's no particular reason why that should be universal. In fact, general critical phenomena arguments suggest that the critical disorder should not. But the exponents, if you can show scaling and show its continuous transition, should actually be universal. So I don't know what the experiments have to say about this. So I don't know who would like to go first.
Maybe since this first question comes from me, let me explain what I had in mind. So when we look at the Stardust transition, say in a 2D Josephson junction network, then there is well defined what are quantum fluctuations. So these are quantum fluctuations of phase which come from the capacitive component of the Hamiltonian. If now in a say continuous film, it is not clear to me what fluctuates. So okay, we know, say at finite temperature we have thermal fluctuations. These vortex anti-vortex paths diffuse and they recombine and so on. But I don't know whether this can be transferred to the 0 temperature state because they should all be frozen out. I don't know what should remain. What type of fluctuation can remain at zero temperature in a homogeneous superconducting film?
If there's emergent granularity, then you do understand how.
Yes, that is so. But that would mean that also, so this only then the same explanation if you say I can the granules assign a phase. And this is again the fluctuating variable. So maybe not everyone agrees with this.
I do.
You do. Yeah.
Why not?
The question is whether say homogeneously disordered.
But I think that we showed many decades ago when I had my hair was a different color. That with completely homogeneous disorder, you get emergent granularity.
Yeah.
So I'm not pushing that. I'm just saying. Sorry. To hold,
Yeah, but if you take now the Fisher paper, there is a talk of quantum fluctuations. What quantum fluctuations did he have in mind? I don't think that he was aware of emergent granularity.
Who was it?
He just made a model.
He just made a model. He was doing quantum field theory. So if you just assume that you have a bosonic system, then you just write down the quantum fluctuations as bosonic. So from a field theory perspective, also it's very natural. But I'm not sure this is necessarily experimentally. Because if the question is okay, so you write down a field theory to describe the universal phenomenon, you should not actually make a one-on-one correlation between what that's saying and what's happening at a microscopic scale. It's some coarse-grained description. Okay.
So you say the question is not very meaningful?
No, if you have emergent granularity, then the question is very meaningful. Right? Then the question is answered, I'm saying.
Yes, okay. Yeah,
but if you don't have, then I don't know what the answer is. It's so easy. Microscopically.
Yeah.
I don't know if that's a satisfactory answer to you, but that is my answer.
No, if you have the same problem than I, then it's nothing elementary that I did overlook.
Know what is the expected critical exponents for different scenarios, or
I think this is tricky. I mean, I think probably people have worked out what the expect. No, I don't think it's really well established. But the experimental question is: do you see scaling? And if you see scaling, do you see universal exponents? That's a reasonable question.
May I rephrase your question?
Yes, please.
You see scaling. Is it a smoking gun evidence of a quantum?
This is a very tricky question, okay? And the reason for this is that when people write down field theories and say these are the critical exponents, they're saying if you are in the asymptotic low temperature critical regime, then this should happen. Then you can ask, how do I know whether I'm in the asymptotic low temperature critical regime, quantum critical regime? Then the answer becomes a little fool.
Can I ask another question really quickly also? People scale the resistance. Is that really a parameter that you can scale? It's not a thermodynamic quantity. Is it right to scale resistance?
Okay, it's a linear response function, I mean, the superfluid stiffness also at some level is a linear response. And we do understand that we can do scaling.
Resistance is kind of, depends on it depends on percolative paths, it depends on.
But these are macroscopic quantities. You're averaging over all of that.
But are there critical exponents for percolation?
Yes.
Yeah, for percolation, yes, but that's
okay.
No, but that's
linear response functions. You see linear response functions.
But experimentally, other than resistance, is there anything else that we have done scaling on?
We don't know when we measured the nodes, we did it on the alpha extra, heat conductivity.
Maybe
kind of show the same scaling down, but
Z nu seems to be all over the place.
From resistance.
Yes.
From resistance, because we made a work with a colleague who was not working on nanowires or even germaniums. Showed that you get a beautiful scaling or 1D scaling on 2D fields and beautiful scaling of 1D data with 2D scale. And the reverse was ugly. So this is my point. Scaling, what can you conclude?
Very good. Maybe actually Aviad is going to offer us ice cream. This would be a good time to burn ice cream rather than discuss this. Unless somebody has something more exciting than ice cream to offer.
I think you can also do scaling with runoff.
Sorry.
You can use runoff.
But it doesn't apply to these superconductor insulated transitions.
If you are very close to the localization, then you start with it's another way to measure your sheet resistance. It's totally related.
It contributes to the normal state resistance.
Is there? But those calculations are all done in regimes. You have to ask where, but
it's perturbative, but it goes, towards the exponential. It's localized.
It's not enough.
Yeah.
But they're done in a very controlled, beautiful way, far from this transition.
But surprisingly, they work up to one quantum of distance.
Maybe so, but you're already pushing them beyond the regime of validity, and the transition itself is definitely outside.
Well, the transition itself, you get the other quantum corrections that come from superconducting fluctuations, and altogether it makes a very consistent picture.
Which algorithm is that? With localization?
With localization and time.
And the interaction.
The logarithm increase in temperature.
And
the logarithmic increase in temperature that you have always.
Actually, I must say that Wittgenstein theory go beyond that.
Beyond that,
probably, yeah, it should.
No problem.
Actually, it does. No, Wittgenstein theory definitely goes beyond. I agree.
That's just they make the first order correction and it goes to infinitum in some sense. So that. Of course, yeah.
So they have made fits to Wittgenstein's theory, and
so it includes that theory includes.
Yeah.
Actually,
would somebody like to conclude?
How does one define a fast order transition in the SID? Is it a discontinuity in the ground state energy?
So what we observe in indium oxide looked superfit density, superfit stiffness as a function of T zone, is that it does not diverge as a power law at the critical disorder. Instead, it flattens and saturates to a certain value, 0.5 Kelvin, which is not small, because I said before that we could measure in magnetic field superfit stiffness. And this is the point. TC, as well as the superfit stiffness, saturates at typically 0.5 Kelvin in amorphous indium oxide. We have another example where this has been seen partially is granular aluminum, where there is also granular aluminum makes a sort of dome, high disorder TC decreases, but then suddenly you cannot get a TC between a certain value and zero. And also people have looked extensively superconducting resonators from circuit QED, qubits business with high inductance. Inductance shows the same, an increase, and suddenly, say, superfit stiffness decreases and then saturates in a similar fashion. Two materials, two examples. It's not a generality. Perhaps there are specific features.
Yes, it saturates, but then eventually just goes to zero. So there's a jump.
Then you see no superconductivity in transport. You have this reentrant insulator, which is possibly a new state, live state. And no resonance in the resonators, but that's you can always say this is not because you don't see it.
So on this point, I have just one more thing. So let's say I take a film of niobium, a very clean film, 3D film of niobium, and I measure the resistance.
Yes.
It will show an extremely sharp discontinuity. And following this logic, I can say that I have an extremely sharp discontinuity, but it's
discontinuity in resistance.
Yeah.
Resistance is not your order parameter.
So this can be
discontinuity in superfluid density.
So this can be linked to the order.
NTC.
Resistance is nothing.
Yeah, no, this
Resistance
I completely agree. So here this can be linked to the energy, like a thermodynamic potential.
So it's a superfluid density, which will be, if you want the mod square of the wave Ginsburg and the order parameter.
Which is absolutely not.
It's delta, you would say.
It is not that either. I mean, you know. Okay, anyway, we don't need to go into that.
But there is one small catch in the experiments where you see that small drop in the superfluid density. Is that superfluid density that is measured at gigahertz?
Yes.
So ideally, you should measure it at much lower frequency. This suspicion came to me only very recently when I was measuring the superfluid density with our resonator method in gigahertz. What we observe is that for very thin films, for thicker films, and low disordered thicker film, we have the superfluid density that is exactly same when we measure with 2-coil Lemberger method at kilohertz and when we measure with a resonator at 5 gigahertz. But when we go to very thin films, about 3 nanometer or so, we see that these values are a factor of 2 difference. So that is what makes.
So you get a much larger superfluid stiffness at gigahertz.
No, for these samples we get a 4 times smaller.
So that would mean it would be even higher at the jump. Okay.
That is true. That is
so
actually
measure with.
But what I mean to say is that they are not the same.
Yeah, probably.
My systems are not close to SIT. These are systems actually that shows the cluster transition, the 3 nanometer kind of film. So there, of course, I don't know the reason. One of the reasons that I'm thinking about is whether tightly bound vortex-anti-vortex pairs, much below kT, can still give me a superfluid response at high frequencies, at gigahertz frequency. But I don't know.
You mentioned 2 frequencies or several frequencies? Like
That's the problem. Right now, we have a method to measure at kilohertz and at gigahertz.
Yes.
I really need to find out something to measure.
Yeah. So what I was going to say was in the case of superfluid helium measurements, Amberg-Amper, Halperin, Nelson, and CGI have a very detailed theory of how the frequency of the torsional oscillator impacts the broadening of the transition.
Broadening of the transition is okay, but low temperature value, does it affect? That's the question.
That I don't remember. I don't think it does because, but I may be wrong. I don't remember that. But you know the results of who was it, Bishop and Reppy, they didn't see a jump discount. Yeah. They saw a broadening, which these people fitted precisely to the frequency of light.
Yeah, that one I am aware of. That is
to command the superfluid density value we get. We got equal or approximately to TC, so maybe lower. This is one point. Can they be higher? I don't know the measurements, but I think also that it's very difficult for the audience to capture things since we are not showing the data. So,
I mean, would you like to? I mean, we can certainly do that if people want to.
They want ice cream.
No, but they can have ice cream and then you can show the ice cream later.
Certainly, the data are much more expensive.
Yes, I think so.
Please, yes.
So, from your understanding of what SIT, etc., is based on, so it's based on controlling the disorder with experimental knobs like magnetic field, thickness, etc. In my case, I work on nickelate thin films, where the disorder is induced by a phase change, structural phase change, that I do not control. Like my disorder is uncontrolled in my case. How does it affect how we can understand the systems, this control versus control disorder, and what features can I get from the studied with my systems. Okay. I'm clear.
Your system looks so bad. Normal. So right.
If you want to get a really nice poster to speak about tomorrow or Wednesday.
And also no facility sorry, concerning the anomalous metal state. With my system, I cannot say anything the fact that I measure distance versus temperature and I see a plateau. It does not mean anything in my case between it can just be a percolating state which is non-existing and I have to go through some metallic portions of the sample. I am right about it, or can I still extract?
That's one possible scenario, and the question we discussed is how to distinguish between all these possible scenarios. This one is tricky. You know, in crystals, people measure the superconducting fraction. So how do you do that in thinking?
Yes, please. I have a really stupid question for you, Papa. It's what's about you to make actually a millimeter size resonator? That the frequency will be less low.
Excuse me?
If you increase the capacitance and the inductance greatly, it's just resonator bigger. Technically, the frequency is way lower, so you go from a gigahertz range to 100 of megahertz range, And because it's superconducting, it's just that it's millimeter size after that.
Oh, you mean
there is no problem
to reduce the
frequency?
Yeah. So it's true. You can, in principle, do it. The problem is in the method that way. So we have these lambda by 2 resonators, which are capacitively coupled, and we measure with a vector network analyzer. So this capacitive coupling requires. So this capacitive coupling will depend essentially on the frequency at which you are measuring. We can go down to possibly somewhat below 1 gigahertz, maybe about half gigahertz, 500 megahertz. Below that, it's difficult to do with this method. There may be other methods like yours.
You can make 1 meter long resonator. There is strictly no limit for that. You will get low frequency.
Thanks to the qubit property, our fridges are
exactly.
It becomes a practical thing. So you already use a meander to reduce the frequency and get higher harmonics. So that's where we cover 1 to 10 gigahertz or something.
You mentioned the sudden breakdown in phase stiffness that you observe. I've read the paper, it's really nice. I happen to know that Christoph does not see this, or at least not that pronounced. Is there any thought on what the difference might be between samples? Why this looks really different?
Can you repeat the difference we have?
So as far as I understand it, in your sample, when you come close to the SIT in terms of disorder, your phase stiffness does not go towards 0, but it saturates some finite value and then seems to break down. Okay. I think Christoph does not really see something like that.
So then,
this is a bit too strongly said.
Maybe I
this is a scenario that was with forced IR links. I can try to explain it, but I don't know if this is the truth. So this scenario for this first order transition is that the states per minute superconductivity is a sort of charge glass, per glass, and therefore it has a different order parameter than the superconducting one. So if you take 2 phases that have different order parameter, you make them close together, you have a first order transition. So now comes the question of this per glass order parameter, and they could have some estimates for the energy scale, whatever you call it. And in it, you have Coulomb, so you put dielectric constant. If you put dielectric constant, then you come back to condensed matter, and the materials may have a different one. So some can have a large Coulombic effect, other less, and you may see, may not, stronger, larger, smaller jump at the transition. This is how I interpret these differences. in light of this theory that it's just a theory. This is just observation.
The idea would be that basically, like every material shows this, but sometimes on.
We are talking about an insulator after when you kill superconductivity. You need to have an insulator to have this.
Yeah, of course, yes.
If you take molybdenum germanium, it's you end up with a bad metal. Yeah, you see disordered metal. So this is not the same story.
Which is that a classical critical phenomenon, it is very well known that if you have first order phase transition, then the presence of disorder actually makes it continuous.
Yes,
which is the
argument.
And this is extremely well established by the work of John Hardy and others.
Yes.
Now, I do know of one example where this might actually be true in a superconductor insulator transition. It's not a particularly well understood example, but experimentally very well studied. So if you underdope cuprates, okay, then there's work from Tom Lemberger, and there is work from Bond and Hardy. That if you underdope thin films of cuprates, or in the case of Bond and Hardy, single crystals of cuprates, then the superfluid density goes to 0. The TC also goes to 0. And both groups see very beautiful quantum critical scaling, which we can discuss. And this is a bit strange because when you underdope and destroy superconductivity completely, you're presumably going into some insulating state with weird magnetism. And just as you said, it's very unusual for two states with two different broken symmetries to come together at a critical point. Normally, you would expect them to be first order. I think the only way we really think this could possibly be happening is these samples are obviously disordered when you're underdoping, and whatever underlying first order phase transition was got converted into continuous.
Yeah, so we have discussed this very famous argument. Unfortunately, I forgot the arguments. I think we discussed it later. Perhaps something you remember. I forgot.
Not in a way that I can cite right now.
But if the first order transition is correct, then the scalings must be wrong.
Yes.
There is no scaling.
Absolutely, there should be no scaling.
But in SIT to get scaling, to have as a function of temperature, flat resistance. In indium oxide, it goes up and down. Where is the?
I mean, so the resistance scaling is probably not also the difficult topic, but say when you want to update specifics. So the question is how deep you can go towards the presumed quantitative point until this other state takes over. Could be that something similar happens in the both materials, and maybe we go a bit farther toward the point, but then also we see this reentrant behavior in the resistance, which seems to indicate that eventually it's not continuously vanishing. And I think the difficulty is that you have so few points at the critical regime. So now we are in 1910, so concerning experimental status, and future will show whether we can more accurately map out this area and see what other things.
That answer.